Hi, welcome to this presentation. Today I'm going to talk about an interesting problem related to encryption and integrity checking. This is approached in a different way. I will first start with the problem statement, and then I will talk about the constructions details. Okay. So what is the problem? The problem is that we are asked to encrypt a list of messages using traditional cipher modes like counter mode or CBC mode, for example. In addition, we are asked to provide integrity as well. So if somebody modifies our ciphertext, we should be able to detect that problem. Okay. The assumptions are, there's only one assumption in fact here. All messages are unique. So you have a list of messages, all of them are unique. Okay, so what are the constraints we have? We don't have space for storing integrity or MAC tag. MAC stands for Message Authentication Code. They also ask us to avoid generating random IVs because the messages are unique anyway, so there's not much value of generating a random IV again. So these are the two constraints we have. The message uniqueness could come from multiple places. For example, you have a list of unique numbers, like credit card numbers or it could be a list of user IDs that are unique, or it could be just a list of keys that you wanted to encrypt and store it, like a key wrapping, something like that. Okay, so there are many cases where messages can be unique. Okay, so the challenge is to not only encrypt but also to provide integrity, but at the same time we should not be storing the integrity tag. So that sounds like a contradiction, but surprisingly we can achieve this actually using an encryption mode that I'm going to talk about. The high-level scheme name is called Deterministic Authentication Encryption. Okay, it's called DAE, which stands for Deterministic Authenticated Encryption. Okay. So before I get into the details of the code and how we can implement this scheme, I'm going to pull a nice paper, a research paper, and walk you through the high-level structure of DAE. Okay, so the paper is written by Professor Raghuve, and this is the construction. We can now look into the details of the construction. So what we are seeing is the left side is the encryption part, and the right side is the left side. The left side is the encryption part, and the right side is the decryption part. Okay, so let's start with the left side first. What are these H's? The H1, HM is basically plain text header information, like metadata. You know, things. It could be like your message ID or something that's not confidential, like a metadata that you would like to add to your data. So X itself is the data that you would like to encrypt. X must be the confidential message you wanted to hide. Okay. In traditional counter mode or CBC mode, you would be generating a random IV, usually random IV, and then you would encrypt using an encryption scheme that we are seeing here, right? Okay, so in this construction, the approach is slightly different. We are not going to generate a random IV. We are going to use something slightly different. What we're doing here is that we use a function f, which is a pseudo-random function. I will show you a concrete implementation of f in a moment. It could be HMAC, for example. What we are doing here is that we take the header messages, right? H1 to HM is header, and then the plain text X. We send this as input to the HMAC function. HMAC will give us an output IV. We feed that IV to our regular encryption scheme. So that's basically what we are doing for encryption. And then we get the ciphertext. Okay. So you have to pay close attention to some of the details. Like for example, K1 and K2 here. We see K1 and we see K2. These are two different keys we need for the scheme to work. So essentially what we're doing is we are generating an IV for each message, right? If the message is X, we get an IV. If the message is say X prime or X2, we get a different IV. So every message will have a different IV. That's how we generate unique IV. Okay, which is often a requirement for many standard existing modes. All right. So what about the decryption side? As I mentioned earlier, H1 to HM is sent in clear text, so that's like additional metadata. It's optional. If you don't like it, you can leave it as empty. The way the decryption works is, of course, the decryption function has to work on the same key that was used for encryption. However, in this time, we don't need to derive the IV because the IV is sent by the sender, right, or the encryptor. So we can take the IV, we can take the ciphertext, send it to the decryption function, and if everything goes fine, we will get back exactly the same plain text that was encrypted. Okay. So far, we have not talked about integrity checking. How are we going to do the integrity checking? We will have to do a small trick here. It's a really beautiful trick. The trick is this. Let's assume everything goes okay for a moment. So what we got is now the X, right, which was encrypted by the sender. We feed the same X here to the function fk1, which was the same function used here, right? What is the output coming from fk1? Is an IV. And then now we check whether this IV is the same as the IV that was sent by the sender. Okay. If the IVs don't match, what can we say? It could be that either the headers are corrupted or the ciphertext C was corrupted, right? Otherwise, there is no way the IVs will mismatch usually. So this is the simple trick we can do to check that the headers, neither the headers nor the IVs or the plain text messages, in this case the ciphertext rather, are modified by the man in the middle. Okay, so that's basically the approach. So let me summarize this here. Our algorithm, the algorithm that is shown here, takes two keys as input, K1 and K2. It takes the metadata H and access the plain text. Okay, it uses a hash function. You can imagine like a HMAC function, right? F is the pseudo random function. Takes the metadata and your plain text to produce an IV, and then it calls your regular encryption function to produce the ciphertext, and then it sends the IV and the ciphertext ciphertext C to the receiver. Of course, the receiver must also get the same header. Okay, so the receiver gets the header as well as the ciphertext together with IV, and then we check whether the input or the received ciphertext is smaller than the block length. If it is, then we say it's right away it can't be true, because remember the Y itself is basically taking the ciphertext, so it can't be smaller than the block length anyways. Then we go ahead and can derive an IV from, okay, first of all, we will use the IV that we received from the sender by just taking the first n bytes, right? And then we take the remaining bytes from Y to make the ciphertext C, and we decrypt the ciphertext C. Hopefully we obtain the same X, and then this part is the integrity checking part. Okay, this basically is computing the IV by following the same steps the sender followed, and then checks whether the two IVs match. If they match, we know it's good. Otherwise, we cancel out. Okay. So I have implemented something closer to this myself, just for proof of concept. I didn't check this part. I should have added that. Anyway, so I will show you the code now. So let's start with the encryption first. Encryption takes the metadata and the data X to produce an IV and the ciphertext. So I call it Deterministic Authenticated Encryption. So I have, say, two credit card numbers in this case. They are unique, of course. And I am going to use the counter mode as an example. I could have chosen CBC also, but counter mode is much easier for me to explain. Okay, so what are we doing first? We generate the AES key, which is the key K1 on the picture, right? This is the first key. But then we need a second key. So the second key itself is generated in this case in a simple way. We apply HMAC on the point 0. Okay, So we basically evaluate HMAC of 0 using the key K1 to derive key K2. So you could have applied any other technique. For example, you could have applied HKDF hash key derivation function. That should also be working. Okay. So anyway, we need two different keys, K1 and K2. So that's the first part. And then again, optional header. I just have a simple header from DG and then a number I, the header. And then the next step is, let's get back to the picture. So we are following the clear picture. So we got two keys, K1 and K2. We have also the header. And now we are going to generate this IV first. First step is to generate the IV, right? So how are we doing that? In order to generate the IV, we need to call the function f on the picture, right? The f, I'm going to make it as HMAC function, okay? HMAC is a pseudo-random function as far as we know. So I'm going to apply HMAC on key K2 together with the header and the plain text message. That will give me some kind of a digest. And then I take only a few bytes of the digest because the output of HMAC is larger than the block length. In our case, we need only 16 bytes. So we just select 16 bytes of the digest to convert into an IV. So basically, we are done producing an IV so far. Now we have IV, we have the plain text, we can call the encryption function. So let's see, yeah, you have a plain text, you have the key K1 and IV to produce the ciphertext. This encrypt is a regular AES encrypt function, right? The counter mode, nothing specific. So we have seen this several times. All right, so this is the encrypt part. What about the data that we are sending to the decryptor or the receiver? We are sending the header in clear text. There's we can see that header is not part of encryption call, right? It's clear text header and clear text IV, of course, IV is public. And then the ciphertext that we got from encryption of the plain text. So we send this to the receiver. The receiver has to decrypt it. We have to assume that the receiver has the same key K1, otherwise this whole thing is not going to work anyways. Now the receiver has to, of course, also derive the key K2, right? In this case, I'm using the same a variable K2 for the receiver. Otherwise, the receiver would also have to do this particular call, right? He has to call the HMAC. He knows the K1 and he will evaluate at 0.0 to get the key K2. So the receiver has to also have the same key K2. All right, what are we doing? We will have to decrypt it. I mean, the receiver has to decrypt it. So how is the receiver decrypting it? Since I'm talking about counter mode, in counter mode, there's no difference between encrypt and decrypt. So I can very well call the encrypt. And then I get the plain text. Okay. So now, where are we on the picture? We actually got the X. We took the ciphertext and IV. We called the decrypt function. We got X. Let's go ahead and check the integrity. Okay. So the integrity part is here. We take the key K2. We append the header and the plain text. We obtain the test digest, right? And then we chop off the necessary bytes because the IV has to be only 16 bytes in our case. And then we check whether the IV we received is equal to the IV we obtained based on the plain text that we got after decrypting the incoming ciphertext. Okay, so that's all. Now let's compile and run it for us to see how this thing works. Okay, so let me walk you through this. So here is the plain text header, right? As I said, message and then some number in the end, like this is the only number that is changing, right? The rest is the same because I just put a simple header for demo purpose. And then the IV, which is message specific, right? And the ciphertext is the encryption of the message. And here is the message the receiver got after decrypting the ciphertext. Okay, for the first message, which was exactly what I shown in the code. And the same thing for the second message. It has the header and a new IV, which is different from the IV here because it's a different message. And then you get the ciphertext also, right? Different ciphertext. And the receiver is able to decrypt and obtain the plain text. Okay, let's now pretend that somebody is modifying the data that is exchanged between the sender and the receiver, right? man in the middle, or some people call monkey in the middle. Okay, let's modify this very quickly. Say, for example, the monkey has decided to modify the header, right? Let's say the monkey modified the first byte of the header. Okay, will this Will this be detected? Let's see. See here, integrity problem. That's good. The system detected that because it compares whether the received IV is the same as the IV it derived after decrypting the plain text, and is equal is a little equal method, right? It compares the two arrays in constant time, and then we check whether they match or not, and then we conclude it was a problem. So we could detect problems with integrity. For example, if somebody modifies the header, what if I modify the IV itself now? Okay, hopefully that should also work. Yep. If I modify the IV, you see here, integrity problem. Of course, in counter mode, if IV is modified, the whole thing is gibberish. Okay, that's why you see gibberish over here and over here. Okay, so let's move on to the next part of the attack, where we modify the ciphertext itself. Let's modify the ciphertext. Okay, well, in counter mode, if you modify the ciphertext, only that particular byte will be affected. So, however, the integrity problem should be detectable, right? Yep, you can see our credit card number looks almost okay, except the first byte, which has a U, because I modified the first byte of the ciphertext. And the same for the second one. The first byte is corrupted, the rest looks the same. Okay, the rest looks good. However, most important is the integrity problem is detected. So, why was this problem detected? It was detected because somebody modified the ciphertext, and the decryption algorithm derived an X which is different from the X that was sent. Therefore, once we feed that modified X to the HMAC function F, right, in this picture, we get a different IV which turned out to be different from the IV that we received. Therefore, the integrity problem was detected. All right, that's basically it. Okay, so I will just delete this to make sure it's working correct. So the key points I wanted to share with you is that we can achieve integrity without having an explicit tag, right? This is what the problem statement mentioned here, that no space for storing the MAC tag. So we solved that problem. We also avoid generating random IVs because in our case, all messages are unique. So why do we need to have an IV? Again, a call to a random number, which may be expensive in some systems. Okay, so this is a nice approach for deterministic authenticated encryption. The approach itself is extremely simple, as long as we can make sure that we use two different keys, and of course from one key we can derive another key using either key derivation function or the HMAC of key K1 followed by value 0, meaning we compute something like this, right? Let's see one moment. So we computed something like this. Key K2 was derived or whatever. I think my K1 and K2 are swapped in the code, but anyway, you have one key. You could derive another key very easily. Let's say K2 is equal to HMAC of K1, 0, right? 0 byte. We'll give you another key. If you don't like this, you can also use HKDF, right? K1, salt is 0. You can set the salt to be 0. And there is also info, which is optional. We can say simple. That should give you, there are some extra parameters like name of the algorithm and so on. But anyway, this will also give you a way to derive one key from another key. All right, that's pretty much what I wanted to show to you. However, you need to make sure that, of course, the receiver also has the same key K2, right? Otherwise, the decryption won't even work. And after you decrypt it, you're going to check the integrity here. So this is not exactly the same as the approach we have seen in other presentations. Here it's reverse. First, we finish the decryption of the plain of the ciphertext, and then we check the integrity. Okay, this is yet another different, interesting approach. So the benefit though is that we don't have to store the tag, the integrity tag, anywhere. Okay. That's all. Thank you very much.